All right, Michael, how about you?
I My parents are in Nelson. I'm recently from the UK,
Okay, where in the UK?
Biggleswade. It's near Bedfordshire,
Ah,
just north of London.
uh-huh. I know Bedfordshire.
I was 7 when I left, so geography is not very good.
Okay. So you, which do you claim? Do you claim to be a Kiwi or to be a Paul? Huh? Okay. Okay.
Been here longer, but still.
Okay. And you're associating with Kiwis and
I know.
Oz here? Yeah.
I
Okay.
did my undergrad
Okay.
here in engineering in mechatronics.
Oh yeah. Okay. And mechanical?
Mechatronics.
Mechatronics. Yeah. Mhm. Yeah. And what you want to be when you grow up?
I want to work with robots.
Really? You've gotten seduced.
Yeah.
Uh-huh. Addicted.
I welcome my robot overlords.
Mm. Yeah. All right. Okay. All right. How about you, James?
I from Tasmania. Well, born in Sydney, but lived in Tasmania all my life. I did a Bachelor of Surveying and Spatial Sciences, which is essentially a surveying degree with some other spatial information on the side of it, so
Mhm.
GIS and remote sensing, GPS, photogrammetry, that kind of thing. Quite maths heavy.
Mm-hmm.
And then I've been went and did surveying for a while and found that cutting through the bush with a slash hook wasn't exactly what I'd envisioned for myself. Um, and so, yeah, I went back and asked what they wanted to go back and do education, asked what they wanted me to do, and they said augmented reality. Someone suggested it, got into it, and I really like it.
Mm-hmm.
And yeah,
Here you are.
I'm over here now.
Well, some of your colleagues are probably going to be joining us in July from the Hit Lab, Australia.
Oh, cool. I go back to Tasmania at the end of the coursework.
Mm-hmm.
So I've got to come back a couple of times
Uh-huh.
anyway.
Okay. Very good.
Yeah.
And so, what do you want to do when you?
I've always wanted to get a job at Google, but
Mm-hmm.
Mark said ICO is better.
Mm.
But at the moment, it's just focusing on getting this stuff done.
Mm-hmm. Yeah. Very good. Okay. Well, let me give you a little introduction about me. I sort of I don't have one home anymore. We have sort of three homes. Um, one here, one in Seattle, and one in Canada. And so we sort of rotate around throughout the year. And when it sort of gets a little cold in one place, we move on to the next one and things like that. But my early background, mostly my academic background, is in electrical engineering, and I did master's work in electrical engineering at Ohio State. But my PhD I received in England at the University of Southampton in England in engineering and applied science. I actually did my PhD while I was working for the Air Force. So the first 23 years, first half of my career, was working for the Department of Defense, primarily the Air Force at Wright-Patterson Air Force Base, and I was designing fighter cockpits, and I worked on these airplanes. I flew in these airplanes. I developed stuff and then tested it and things like that. And one of the things that came out of my work was we basically invented what is known today as virtual reality. We were the first to actually do it, and actually we were flying it and using it for simulation and things like that. Then other guys came along on the outside. The super cockpit I'll be talking a little bit about later on, and but prior to becoming a one of these military guys, I actually worked on a production line. I was as soon as I graduated from with my bachelor's degree, I went to work for Procter and Gamble, and I actually I was working running a production line at Procter and Gamble in Cincinnati, Ohio, where they made Scope mouthwash. And let me tell you, that was quite an educational experience. That a raw recruit coming right out of university and going into a production line. This is a brand new line that they were just starting up. So I've worked now, it's now about 46 years on user interfaces. But the neat thing I can say is that I've really done it. You know, I'm not just read about it and read a book and then taught a course and things like that. I've sort of been out there doing it and testing it and that kind of thing. So the raw real world experience is there behind it. So this is what I was working on. I was working on these very complex machines where you had 50 computers and you had in the cockpit you had one operator that was trying to operate these 50 computers while moving this aircraft at twice the speed of sound and pulling G's at the boundaries of consciousness and being shot at the same time. Probably the busiest workplace in the world. And the consequences for making a mistake are pretty big. So this was sort of an energy delivery machine from point A to point B. And this is one of the cockpits that I worked on, this original F-15 cockpit. But then, you know, we decided that we were going to revolutionize this with new technology. And then this is what the new F-15 cockpit looks like with all kinds of electronic displays. And we thought this would be a great advance in technology and using this technology, all color, all this kind of thing. Well, let me tell you, it wasn't. If anything, it made the pilot's life a lot more complicated. And I'll explain later on why. So all of this migrated to things like the new Raptor, and where the cockpits even get more electronic and more, and this head-up display is one of the things that I worked on a lot. So that was my past. Present then, about 23 years ago, I decided to become an academic and beat my sword into a plowshare. And I left my laboratory at Wright-Patterson Air Force Base and started out as a professor. I thought, gosh, this will be an easy life. I'll just kick back and think great thoughts and, you know, and mentor a few students, teach a few courses. What a great job, you know. I had no idea how hard the professors work. And because it's not like you have just one job, you have like 3 or 4 jobs. You're spending all your time writing proposals, you're teaching these courses, you're writing papers, you're mentoring students, you're serving on professional committees, you're going to conferences and then trying to you're begging all the time. But it's been an interesting, exciting life. So I'm in a department. My primary appointment is in industrial engineering at the University of Washington, but I have adjunct appointments and students from electrical engineering, from mechanical engineering, from aero and astro, and human-centered design and engineering. I'm an adjunct professor here and also in Australia at the University of Tasmania. So I started, when I moved from the Air Force to University of Washington, I started this lab called the HIT Lab, the Human Interface Technology Lab, based upon a lot of the things I was doing for the military. But what I wanted to do was take those things and actually build better ways for people to interact with machines, not only for, you know, the military side, but for education and medicine and entertainment and that kind of thing. And that became the mandate that I worked on. And so I started from scratch, one guy, in this new environment, some funding from the state of Washington, and a building, part of a building, new building I could go into. And we grew to 120 people, and including staff and students, including Mark Billinghurst and Win Yu and Henry Dew and all the other original gang. And with an interesting mandate that what my job was is not only to be a professor in the College of Engineering, but to run this laboratory that was actually funded by the state of Washington Department of Trade and Economic Development. It was intended to be a bridge organization that would take the technology that we generated in the lab and provide a pathway to industry. And so my report card from the lab standpoint was just how many companies did you start? How many patents did you generate? How many people are employed in those companies? And that was the model that we had. This is a little old slide. This is we actually started 26 companies, and with students like you guys. And 2 of those companies are traded on NASDAQ at a market cap of over $10 billion. And this is done with students. I mean, my students are out there driving, you know, Mercedes and Beamers and things like that, and into the student parking lot, you know, which is it's a little different. But so along the way, a number of patents. I have about, that says 12, I have 16 now. One of my patents was the virtual retinal display. This is where you scan an image directly on the retina of the eye, and there is no display screen anymore. And we spun off a company called Microvision that makes those things, and several other companies like that based upon my patents. I'll be talking about some of those as we go along. And I do a lot of consulting, and in addition to coming here part of the year and going to visit Tasmania and that kind of thing, I do a lot of consulting. I have my own lab, my own private lab. That's my own sandbox. I call a RAT lab. It stands for Rocking and Thinking. And I bought a house down the street where I live in Seattle, and I just chocked it full of electronics. And I hire high school dropouts or anybody I want to. And we're makers. We make stuff. And it's so fun. I don't have to justify who I hire. I don't have to justify what I buy. Except my wife. My wife says, this is an expensive hobby you have here. And I say, well, yeah, but we're doing good stuff. But so I have a lot of fun. Rat Lab, also AR2 Works, which is the original company that provided AR libraries. Mark and I founded in 2002, and it still exists and it's still operating and that kind of thing. So here's my family. I have 2 daughters. They're right here. There's Kim and there's Cindy. And then I have 4 grandkids. And there's my wife with the purple hair. And so that's a little bit about me. Okay, now I'm going to give you your first interface design task. And I'm going to give you 5 minutes to do this design task. Right, you ready? You're going to need a piece of paper. Once you take a piece of paper, all right, and this is your design task. So I'm going to give you 5 minutes to design a wheelchair for a person who's blind. Okay? Starting now. You have 5 minutes. You guys can do it too, by the way. We can collaborate. You can. Yeah. Dynamic control? Yeah. Uh-huh. You can't play then.
What's up a handicap?
Mm-hmm. And so you have a handicap. So you can sketch, you can describe, you can you can use whatever you want to do, words or drawings or whatever. Don't give it away, Rory.
Got to.
Okay, I have about 3 minutes left.
I tend to design ridiculous things.
Okay, 2 minutes. One minute. Ten seconds. Okay. So hand them in to me here.
Mine are ridiculous.
All right.
Sorry about the scribble.
But you need to see the other one. I've got two. I have two.
You have two. Yeah. Okay, interesting. All right, now, okay. Oh, okay, thank you. Thank you, guys. Okay, you don't have, okay. So no one tear the back out of your thing. Okay. Interesting, okay. I'm going to hang on these a little bit, by the way, guys. So I have some questions for you. So what was the first thing that popped into your mind? What was the first thing you thought about that popped into your mind when I asked you this question?
That they can't see.
Say?
The fact that they can't see.
Okay. So what did you see in your mind?
Nothing. They can't
How
see.
keep people for
Sorry?
how keep people for sites.
Yeah.
Like
Okay. So you want them to be able to see, even though they couldn't see.
wheelchair would be able to see.
Okay. All right. All right. Did you think about putting yourself in their place, what it would be like to sit in the wheelchair and, okay? It's interesting that when you have a design problem, and as you interface designers, you'll have, in many cases, design problems given to you that you're not familiar with, and at least starting out, and you have to learn. And probably you made some assumptions, right? As a matter of fact, in looking at your wheelchairs here, Of course, I called it a wheelchair so that they all have wheels.
Mine has tracks.
Yours has tracks, that's right. It does have tracks. That's right. It looks like a bulldozer.
Yes.
Yes. That's right. That's like one solution, isn't it? Yeah. And so you have to start off with some kind of assumptions. And usually that assumption is that it's based upon something you've seen or something that you've had an experience, a personal experience. You start off with that and then you build from there. Or maybe there's someone that you know or something that you've actually seen through some kind of media. The question is, are these assumptions that you make valid? That's still your starting point. You can't help it. You're not responsible for what your starting point is. But let's face it, when you start off, you do have some limitations. What are some of the limitations that you have, your deficiencies, in addressing this problem?
You're not blind.
Exactly. You're not blind yourself. What are some of the others?
In a wheelchair.
Okay, what else?
If you're basing your design off something that you've already seen or experienced, then you might be limiting it to what could be done.
Yeah. I mean, obviously, we're talking about intervention technology here. And what technology do you use? I mean, it may be that it doesn't exist, or whatever, the sensors don't exist, or whatever you need to do to get there. So you really have a lack of personal experience because you're not blind and you're not in a wheelchair. And perhaps you have a lack of knowledge of really what's going on out there with the user population. Where do they go in their wheelchair? You know, what about just moving around in the house? Getting to the street or going to the market. Probably don't go to the movies too much, but nevertheless, that's, you have that lack of knowledge. Perhaps another thing that you don't have is, at this point in time, the reason you're here is because you're trying to gain some knowledge about how do you design interfaces. And so perhaps there's some limitations that you have right now until you finish this course, and then of course you'll all be experts in that. And lack of practice. And hopefully this at least is part of the journey that you're taking, so that you'll be in a position to know how to systematically address issues like that. But nothing takes the pace of experience, actually getting out there and doing it. I don't care how much book learning you have. It's actually doing it that's where you learn about what's going on. So in the case of this wheelchair, there also, when you get into the act of designing, you can look at different ways. I mean, there are the so-called evolutionary designs that pretty much build upon what's already there. But then there are these paradigm shifts, like your tracked vehicle, or one that doesn't have wheels at all. Who knows, you might even have an air cushion vehicle or something like that we move around with bumpers all around it and things like that. I mean, really that's the so-called lateral thinking or out-of-the-box thinking. And the revolutionary design sometimes sort of shakes things up a bit so that you think in different ways about it. Sometimes we're really restricted with the narrowness in which we approach these design problems. And then you get into these paradigm shifts of where, let's say that you add a new modality that hasn't been there before, like automation. Like you just tell it where you want to go, and it takes you there, avoiding all the obstacles, and avoiding all the traffic on the road and everything. And it's full automation. That would be something that probably hasn't been done yet. Yeah.
Hot air balloon and a guide crow.
Sorry?
Hot air balloon and a guide crow.
There you go. See? Yeah. Or beaming. Why not just use a little bit of Star Trek technology and transport you from one place to another?
You're the same person that left.
That's right. You can get scrambled in between. I agree. So tactile displays, about how do you see if you're blind? I mean, there's a lot of work going on in using ultrasound in your walking sticks, to search and find where things are located by transmitting vibration up to the hand. There are now ways that where you can actually replace the retina with artificial devices and implantation into the visual cortex. And so there are a number of things that would be technological possibilities for building this wheelchair. But in the end, you have to sometimes just build it and test it with people who really are blind and see how it works, and then iterate on that design. So in the process of doing this MHIT, you really are getting sort of like drinking from a fire hydrant. You have Adrian and Mark who are working on sort of the technology side from the prototyping side standpoint. You have Andreas that is looking at the evaluation side of things, and Christoph, who's sort of centering on the design part of it. Now, my whole role in this is really a primer on just thinking. How do you think about it? How do you think about human interface design? Because, you've got to encompass everything. You have to encompass the human factors, hardware, software, application, all of it. You even have to get ultimately into the manufacturability, cost effectiveness, life cycle, and those kinds of things.
Emotional response of the user, isn't it?
Yes, and that's one of the things we're going to talk about quite a bit in the UX design. Now, what I plan to do is provide 4 lectures that are, again, based upon my experience and some of the things I believe that you should at least have a feeling for, a sensitivity to, as you go into these other sets of lectures you get from the other guys. Today I'm just going to concentrate on some initial definitions, and I'm sure all the guys are starting with definitions as well, but I'm going to have my own, and mine are probably a little orthogonal to some of the traditional ones. Talk about the human side of human interface technology, and then the machine side, the technology side, and then how do you put them together into various applications, and I'll be showing you a number of applications. My whole game has been pretty much in virtual reality and advanced, very complex machines. And I've built and designed several anesthesia delivery machines for operating rooms and medical surgical simulation devices and things like that. So today, in terms of the agenda, we've had our introductions. I want to start off with some initial definitions and these kind of things, and we'll cover them and give you an assignment to bring for next Thursday. Okay, let's go into some definitions. Let's start off with what I mean by technology. And by the way, you guys will have copies of all these slides. So my definition, my variation of the definition from Encyclopedia Britannica is that technology, the application of scientific knowledge to the practical aims of human life. Note, practical aims of human life. Or, as it is sometimes phrased, to the change and manipulation of the human environment. Now, if you go to the Devil's Dictionary, here's what it says. The Devil's Dictionary: human development of tools and scientific movement toward revolving around laziness, for which the body of human society is willing to step on and mangle. It's the future. Okay, so laziness may be a motivation behind this too. Okay, now what do I mean by tool? Now, tool is a system of technologies that helps the user perform a task or a set of tasks. Okay? This is all sort of self-explanatory almost. But let's look at some self-contained tools. By self-contained, the whole system is sort of there together. All right? Now this is an interesting one, a self-contained tool, because you can actually record and play back your video in one device, although you can play it back in other devices too. And you can say, well, yes, but you have a charger for it, and you have a power company that provides the power, and the water that causes the hydro to work, so you get the power to run the charger to run. So it could be part of the system as well. Here's a neat one: kite flying, kite surfing. Any of you do kite surfing? Well, it's sort of a self-contained thing, although there's Mother Nature that helps out, with it. But then there can be tools that are part of a system. Think about this. So when you got up this morning in the bathroom or in the kitchen, you turned on the water. This was the interface to a system, isn't it? So tell me what the system is. What are the subsystems in that system?
The water under the street, all the pipes and things.
Pipes? What else? Okay, filter and filtration.
Pumps.
Pumps.
Human.
Sorry?
The human.
Well, yeah, the human is a subsystem of the system that's operating this, yes. What about,
The tap.
well, yeah, the tap here. What about the reservoir? Well, where does the water come from?
The sky.
Where does the water come from? Sort of precipitation, right? From moisture in the atmosphere. Where does that come from? And where does that come from? So it's all a part of a system. And as far as the human is concerned, the end game here is the operation of this particular subsystem so that you can get the water and use it for something, right? How about this as a part of a system?
CRT monitor.
So obviously you have the human interface part of it, which is the front surface kind of thing, where you have a controller and you select the channel and adjust the volume and may even record, whatever. What is underneath that?
The
What's back
cathode
behind
ray
it?
tube.
Sorry?
The cathode ray tube.
Well, this one is, but we don't use them anymore, do we? We use LCDs and plasmas and things like the lasers.
I guess the people that make the program.
Ah, that's interesting.
The broadcasting network. The towers.
Yeah.
People that pay for it.
Electric company.
Yeah. So really, this appliance is only one part. I mean, it's a sort of an integration of technology itself, but it is only one component of a larger system. Same can be true with this. Yeah, with your electric lights. When you think about it, all that is back behind the photons that are streaming from that. And then this is a RAPCOM, a radar approach control for the FAA. Wow, there's a lot of stuff behind that.
It says keyboard lighting up depending on the keys.
Well, those are all to perform various functions over there on his left.
Like something like green.
So there are all kinds of electronic devices here. But another part of the system is, of course, the aircraft themselves and their systems, because they have transponders on them. So when the radar is going around sending out signals, it says, "Who are you?" And the airplane says, it gets that signal and it shouts back, "I'm Delta Flight 454." And it shows up on the screen. You see a little triangle and it says DL 454. A lot of things going on to get that to happen. So there are also tools that manipulate matter, right? Here's one of the tools that manipulates matter that we use all the time. Actually, this is a very special matter manipulator. This is actually the executive bathroom between the original offices of Hewlett and Packard in Palo Alto, California. So their offices were adjoining. This is like a shrine now. And this is the toilet that they used. I asked the docent that was there, can I use it? You know, I thought when I sat down on this that something would ooze out of it, and I would get all these great ideas, you know, would come. But she said, oh, no. That's sacred. It's sacred. So I didn't get a chance to interface. Hewlett and Packard, as it were. Yeah. So here are some tools that manipulate bits. These are basically bit manipulators rather than matter manipulators, right? Now it's interesting, and I have these guys here. This is another airplane I worked on. This is the Blackbird SR-71. So why would I call it a bit manipulator?
They took pictures of the...
Yeah, it was a reconnaissance aircraft. So it was actually acquiring bits, photons from the ground, taking pictures, and then they were using those. Then there are tools that manipulate energy. Right? This is a power station control panel, a tank. It basically manipulates energy. And this Phantom, this is actually one of the airplanes I flew on. It manipulates energy. So you have all of these different tools, but they have different connections of their subsystems and different, of course, applications. Okay, now, what do we mean by the interface to the tool? Now, the interface is really a subsystem in the system. And that facilitates the user interaction with the tool. Now, let's go to this next term, interaction. Because we hear a lot of, there's a lot of nebulosity between human interface design, human interaction design, all this kind of thing. To me, interactions are the actions and processes that take place between the human and the tool through the interface. Interface is the thing, and interaction is what you do with the thing to perform these particular tasks. Okay, so it's interesting that when you look in the definition of interface, the definitions, you can divide it into inter and face. It's really what goes on between faces. Between faces, the face of the human and the face of the machine. So, it's really difficult, though, to define where that face is. What is the boundary of that face? For example, God was having a problem with this, too. He says, Peter was trying to advise him here, well, the IT department, Heaven's IT department was trying to say, you just can't punch in, let there be light, without writing code underlying the user interface functions. So there's a lot more to it than just what's on the surface, perhaps. So is this the interface? Is this an interface? Well, yeah. Well, what about this that's behind it? What about this?
Well, I guess it's the interface to know what to do.
What about this? And this? Now, there is a cognitive function associated with interfaces too, but I'm not sure this is the best illustration of it. This is more like cognitive dissonance, but nevertheless. So really the interface, when you think about it, is really not just one face. It's just, there's a whole system within the subsystem that deals with the interface. Let's take, for example, trying to divide these things between the technology and the tool and interface. So here you have a tool, which is basically a matter transporter from one place to another place, right? And the technology that's embedded in this tool is one of the pieces of technology is, of course, the powertrain, the mill, the engine. But then you have this interface for the human to control what happens, control this tool, which has embedded in it all this technology. So here's just another way of looking at it. You know, there's a tool, an interface to the tools, and things like that, and so forth. Sometimes the tool and the interface are embedded, like in a smartphone or in an iPod or something like that. Now, when we talk about the interaction with this tool, you know, it's performing this activity of which through the interface and the use of the technology. Now, this one's fairly simple, isn't it? But when you get to this, it's a lot more complex. Of how do you support the manipulation of all the functions that are here? Take, for example, and this is one of the things I worked on. Here you have a crew member flying along, twice the speed of sound, and looking for some bad guys. Now, the tool in this case is this vehicle that has a power plant and has all kinds of subsystems in it, has weapons, as you see here, Sidewinder missiles and things like that. And the pilot has control sticks and throttles and things like that to control this. But the problem is, this particular interface has some limitations. In order to actually aim these things, like the Sidewinder missile, you sort of have to aim the whole airplane. You have to steer it around to where it's within the so-called gunnery envelope, right? So this is a situation where the pilot is having to perform a function that is very difficult, especially when you're flying fast. And anytime you turn the airplane, guess what happens?
G-forces.
What's that?
G-forces.
G-forces, that's right. So you turn it hard enough, fast enough, tight curve, and guess what? Your G-forces go up really high and may go up to, about 7 Gs, 7 times your own weight. But you're wearing this suit. This is a special suit. In addition to sitting in the ejection seat, you have this special suit on. It's called a G-suit. What happens is, as your acceleration goes up, the G-suit pumps air into bladders that squeezes your legs to keep the blood forced up in your head. Because if the blood drains out of your head, guess what? You black out. And it's not instantaneous. I mean, it's sort of, you get a gray out. You get this narrowing of your vision until you're still conscious and everything, but you see that through this little hole is a hydrostatic column of blood drains out of your head. So you have to keep this G-suit pumped up. And so this is one of the problems I was working on in fighter airplanes. And this particular aircraft, the F-16, is so stable, I mean, so maneuverable. You can go from 1 G to like 6, 7, 8 Gs instantaneously. Not even enough time to pump up the G-suit. And pilots were blacking out instantly in this thing. And not only blacking out, it took a while for them to come back. And then when they blacked out, they didn't remember they'd blacked out. And by that time, the plane is augured into the ground. So one of the things I was trying to figure out is, well, how in the world could you aim the weapons without having to aim the airplane? Because the pilot could see where the bad guys are. So I started now applying technology. What if we could instrument the helmet? What if we could actually determine where the pilot's pointing his head in the side of the cockpit, using a way to triangulate on the helmet? Maybe some photodiodes, infrared photodetectors here, infrared scanners, and you compute and triangulate on those points, and you'd give the pilot a projection of an reticle at optical infinity, and the whole idea is you just position the reticle over the target, and then you determine where these 2 points are on the side of each side of the helmet. You draw a vector through them, and you resolve that vector into azimuth and elevation angles, and then you use that to aim things on the aircraft. So that's what I did. And here I am, Lieutenant Furness, in 1968, wearing the world's first helmet sight system, where you now aim your head at things and and weapons follow. So now you don't have to move the aircraft. And the weapons do the turning and pulling the G's, much rapid. So we had to test this. It's not just good enough to design it, get it to work in the lab, things like that. We had to make sure it worked. So we took one of our airplanes, this is a F-106, and had it out there flying. And then we had this aircraft, another F-106, that had the infrared scanners here, and here's the helmet and the reticle projection, things like that. And we said, just how well can a pilot track with his head these things out there? It blew us away. Even at pulling, when these aircraft are turning, where you're pulling 6, 7 Gs, this guy was tracking with basically a 0 mean error rate. We do a little Kalman filtering on this, and there was a high G buffet. The aircraft sort of vibrating like this when you're at those G levels, but 0 mean error, better than any systems could do actually. So what we did was resolve this problem, where now you just have to look at things. And we added later on eye control. So not only did you move your head, you also looked with your eyes. So we're tracking eye position and head position at the same time. So this was a new interface to subsystems that already existed that transformed the ability of crew members to perform that function. It was just in the interface. All the other technology was there. So that was sort of a complex interface, but you guys run into interfaces every day. Here's an interface. By the way, you know that there's some bad interfaces out there. Doorknobs are basically a bad interface. Why?
You have to put in effort.
It's not standard.
Oh.
Show what you have to do.
Well, yeah, you don't know which way to go, and you don't know, sometimes you don't know whether you push or pull and things like that. Now, this is a very elegant, has a affordance to it. So you know pretty much what you have to do with this particular doorknob or handle, if you want to call it. And you have a way to grip it. You're not putting your hand around a ball and trying to pull. You have a handle to pull. A lot of thought went into that doorknob in terms of the human interface standpoint. And of course, you guys run across these as well. These interfaces for bit manipulators. A lot of transformation has been taking place in that. And you run into these things, these matter manipulators. Have you guys ever tried running a backhoe?
Someone wants
Good fun.
Great fun.
So many levers.
Did you get in there instantaneously and know how to do it?
No.
No.
It took me about an hour before I was proficient enough to actually start using it.
Yeah. Turns out my son-in-law, for my daughter's birthday, gave her a 3-hour time in a backhoe as her birthday present. And she went out and dug holes and filled them back up again, and just had a blast doing that. Some kind of latent thing there, I believe. But it's fairly complex, and when you think about it, you have to spend some time before it really becomes a skill-based performance. Well, one of the things we started playing with in the lab, we had a simulator for a backhoe. You just use your hand. You say, I want to do this. That was sort of intuitive, and it worked. But no self-respecting backhoe operator would you see doing this kind of thing. And this is a problem, because once you get that skill-based behavior, you don't want it to change. Just like the keyboard. Who would want to change the QWERTY keyboard now? The Dvorak keyboard is a much more efficient keyboard. But for an old geezer like me to try to learn how to operate that, it would be not good. So, ultrasound technicians, same thing. The old ultrasound machines had so many controls on them. They knew how to operate it. But the new ultrasound machines were sort of, you push the button and go. And yeah, and the old ultrasound people didn't like it because they said, Oh no, because it made it easier for people to come in and infringe on their territory, the old heads. True with fighter cockpits, really true with fighter cockpits. Boy, the old heads, when you gave them all these continuous computed impact point, what we call a hotline gun sight, we had all these things where it was just intuitive how to operate these things. Even my daughters could fly these things in my simulators. But the old head said, I don't need that. I'm good enough, and they were. But the problem is, they had 2,000, 3,000 hours flying in the aircraft, whereas you have a guy with 100 hours catch up with them with the new technology. So you also have the acceptance of the users. And remember, the users may be a different point in their development. You have to take that into account. And then, of course, there are interfaces for energy manipulators. But interfaces don't stay the same, just like I mentioned with ultrasound and so forth. When we think about bit manipulators, for example, being able to put your ears at another place, which is what a telephone does, is basically put your ears in another place where you can hear people that are in another place. You see this evolution, don't you? The telephone. As a matter of fact, it was interesting that back in about this generation, Western Electric did a study to find out just how large will the telephone system become. And they did a study. This was back in about 1918, and they decided, well, it can only become so large, probably about 3 million subscribers. They figured it'd have, and the reason is, you couldn't have but so many telephone operators. Now, of course, what happened is everybody became a telephone operator. You became your own telephone operator. That was a paradigm shift that changes the whole landscape. And then, of course, there's further evolution of that, even get into touch tone, and then now you carry it around in your pocket. And then here's where the difference between the physical operator. As a matter of fact, you can go down to Ferrymead and see all this stuff. It's really neat to see some of the old gear down at Ferrymead until a modern electronic digital switching system.
Is that stuff still run today?
Yes, they have some. They have some of the old stuff, the old relay switches stuff. Sort of cool. I mean, that's the problem with computers anymore. I mean, computers really used to be fun. You walk into a room, there's a plenum floor, the things are vibrating, the tapes are indexing on it, and you hear the indexing on the discs and things like that, and you see the lights flashing and everything. It was great. I mean, boy, you could feel it. You could feel the energy, You could even hear the core and the magnetic core. You sit next to the machine, you could hear it singing in there. And you can tell what mode the computer is by listening to the singing of the core, Now it's boring.
Field trip.
Yeah. Now we have, of course, the interface has become the thing because the interface is the only face you see when you think about it, of a product. It is, especially an electronic product, it's the only face. So things like not only functionality, efficiency, and effectiveness are important. Also, likability, the emotional connection that you have with this. That becomes more important, like the watch. The watch, pretty much, you don't worry anymore. Mark talks about this a lot. You don't worry about anymore how accurate your watch is. They're all quartz now anyway, and they'll lose a second in a year or something, Nobody worries about it. So you don't care about how good a time it is. As a matter of fact, how many of you guys actually use watches? Okay, well, yeah. Well, usually you go in a classroom, with students, and you only have about, 1/3 of them that raise their hand because they're using their cell phone, of course, for that.
You have to go to your pocket for that.
But what do we do with watches now? What is it about? It's all about a statement that you're making.
Calculated watch.
Yeah. I mean, what about all these covers that people put on their cell phones? It's about fashion. The whole swatch thing was all about, converting watches into these different, bands and things like it. Is that a swatch?
Swatch, yeah.
Yeah. I mean, and they're making a fortune, but it's all fashion. Seems like everything turns to fashion after a while. It's all about likability and about the emotional connection to these things. Yeah. But you look at also some of the transformational aspects that happen in these new interfaces. So is demand for just more and more gadgetry, things like that. But maybe there's some functionality that comes with the new interfaces, like the breakthrough that Nintendo made with the Wii. Going from the old control platform, the old gaming platform, to actually moving your body. Well, yeah, it was sort of a breakthrough, but not as much a breakthrough for these folks as it was for the folks that are in the nursing homes. Because now they can play computer games. Rehabilitation, it's called. Rehabilitation has become a big deal. Now, they can go bowling, they can play tennis, they can do all these kinds of things by natural movement, intuitive movement of their body. And that's what this Wii is, the Kinect is all about, is using natural movement as a control input. So let me tell you, UX design for the next 10 to 20 years is going to be hot, because that's what it's going to be about. What's underneath it, what's inside, the intel inside, it's not as important anymore. It has to provide the functionality, but it's how you get to it and what you have to do and what's intuitive. Okay, so the goal in all of this is to design an interface that makes those interactions with the tool most useful in performing the task. And that sort of devolves into getting bandwidth to the brain, to and from the bits to the brain. So, what does I mean by most useful in that definition of the goal? Well, here's the first thing. It really needs to be intuitive. Nobody reads instruction books anymore. It has to be sort of, you learn really fast just by using it, right? And that requires, to make things simple is complicated and it requires a lot of thought. So it has to be easy to learn. Obviously, it has to be effective. You have to get those tasks done. It needs to be efficient. You want to get those tasks done in some kind of minimum time or minimum expenditure of resources, including your cognitive resources and neuromuscular things, fatigue and things like that. And you need to like it. Well, if you do those four things, and you can make it, obviously you have to be able to make it, then you have a dynamite interface. So, it seems pretty intuitive. Why don't we do that? Well, it's not that easy. Why user interface design? Well, Dilbert dealt with this problem. Dilbert and Alice. So Dilbert, good computer programmer he is, Dilbert says, I designed the user interface myself. How do you like the colors? And this is Alice's response. So Dilbert is concerned. He says, do you have the flu? And she said, interface design. And so Alice is so concerned she goes to the doctor. The doctor says you have chronic Majabus crapus, but that's not why you puked. Why did she puke? Have you been exposed to any user interfaces designed by engineers? Yes. You have interface poisoning. You'll be dead in a week. Well, what is she going to do? Well, she has to go for help. So, yeah, she goes for help. She says, she talks to her sanitary engineer friend, and she says, I have 1 week to live. I've been poisoned by looking at bad user interface design. And of course, the sanitary engineer says, I see a lot of this. The only cure is to crowd out the ugly memory with images of staggering beauty. Where would I? Okay. So the whole solution is you take this course, this master's, and you'll be able to help Alice, the Alices of the world, not puke when they see human interfaces. Okay, let's move on to thinking about this a little more analytically, about where the interface exists and what we have to take into account. I'm going to introduce my so-called Furness box kite model for human interface design. So we start off with a channel. Let's just call this a pipe, like a conduit, okay? On one side of the conduit, we have the so-called human processes. On the other side of the conduit, we have machine processes, and you see things are flowing back and forth through this conduit. Okay, the first thing we're going to do is slice that conduit and put this sort of space between the two. So here we have our human processes, and here we have machine processes. And then what we're going to do is further slice them. So here we have this layer on the machine side that we call the display control unit. It's really a transduction layer. It transduces something from one state to another state. It transduces electrical signals to light. Or it changes electrical signals to mechanical vibrations of the air. Okay, on this side, you have a transduction level we call sensory psychomotor level. Here we have our sensory end organs, which transduce photons into what? Electricity again. Pretty much, electrochemical. Okay? And it changes sound waves into what? Electrical signals. Right. So we have these two transduction layers. Now, what goes across this boundary? What goes across that boundary?
Physical energy?
Yeah, it's all some form of energy. It's not information. It's not data. It's light. It's photons, mechanical vibrations. That's all that goes forth across this boundary. A lot of people say, well, that's the interface. That transduction layer, that's the interface. Well, it isn't all of the interface. Because here you have a processing layer. And the processing layer organizes the way that those transduction things take place, right? Like a pattern of light, a raster scan, or something like that. On the human side, you have this perceptual thing that takes those signals in the brain and organizes those two in what we call perception. We can hear a particular note, frequency, and we can say what that frequency is. And that is a sort of at a perceptual level. And then you go a little bit further, and you get down here at the cognitive level. Cognitive level is where you take what you perceive and you think about it. On the other side, you have, on the machine side, you have what? Well, yeah, I mean, it says it there, doesn't it? It's the program. It's basically the content. It's Oprah. If you're watching the Oprah show, I mean, it's the content that is then manipulated by the processor that is then transduced, put into these patterns of light signals and sound signals, picked up by the human, and goes to the other end. So this first level, this level 1, is what I call the signal level. These are just the transfer of physical signals across the machine and human boundaries. Now, as it turns out, there is another level here. Obviously, on this side, the user builds models in his or her head. We run on models, these models that we build. And so we gain that model of the machine and the world through our experience and through training and a priori knowledge and things like that. And that's, of course, what helps us assign meaning to these cognitive functions. Then these signals come in, can be information. They can't be information until you get to that point of where you're combining it with what you have as experience of some sort. Now here you have an interesting thing. Who are these guys?
That's
You. That's right. Here you are. So now you're trying to figure out a lot of things. First of all, you're trying to figure out what's this. You want to know what's in this guy's head. And what are the functions that are performed here? How do people see and hear? How do they learn? All those kind of things. Because what you're trying to do is design this in order to get something to happen over here. So there's this indirect path, sort of a meta path, where you have to actually almost do a mind meld inside that user, find out what's going on in their head. And this is also based upon what? Experience. You got to have experience too. But you have to have a model of the user and the model of the machine. You have to have another model too. And that is, what is a human going to do with this machine? Because the whole idea is to perform some task. The machine in itself, is worthless unless you can do something with it. Unless you are a Jaguar owner. Now, if you buy a Jaguar, the only reason you'd have a Jaguar is so you can just look at it. Because it sits in the garage and drips oil on your garage floor. And it doesn't move very often. But it's pretty. It's nice. And so that's the reason for having a Jaguar. But most of the time, you want this vehicle to take you to another place, move your body to another place, right? So there's a task to be performed. So the user obviously wants to use this machine to help perform this particular task. And there are all kinds of connections going on here between the user and the task, and how that goes up to help develop this model. Is a loop closed here. And then, of course, the whole idea of the machine, there's also a machine connection to the task, but the designer has to understand the task also and understand how the user is going to perform the task with the machine that they built. So where's the interface, guys? It's the whole thing. You got to take in the whole thing in order to do it. So that's why it's not just, learning a little psychology or learning a little prototyping. You got to put it all together in one big picture to get it to work. Now, one of the things that we do, and I teach a course in user interface design in the U.S., one of the things we try to do is, it's really tough to design for a multitude of users. So what we do is we make up one user, one archetypical user. We call that a persona. This persona is a typical user. All we're doing is design for that person, that one person, and we want to make it perfect for that person. Now, this person is actually an amalgam of a bunch of people, but still, you do it that way, and it helps. So where's the interface? Like we said, it's really everywhere. And now when you get to the links that are going on, the interplay in the interface, you see from the human and machine side, you have this transduction connection between the displays and the senses like hearing and seeing, and the motor control side of things. By the way, there are other transduction things too. We have other things that we send out. What do you think they are? Other signals that we send out as humans.
Body language.
Yeah. What else?
Smell.
That's right. As a matter of fact, smell, of course, is a very powerful, it's like a fingerprint. We have our own pheromone. And that's what bloodhounds use when they're trying to track somebody. I did one of the things in my life in the past, I was, the Air Force was wanted to do some advanced thinking about systems, concepts. So what they did was they hired a whole bunch of science fiction writers, like Asimov and Furness and all these guys, and Niven, And they took a bunch of these guys, science fiction guys, a bunch of futurists, and a bunch of lab pukes like me. And they locked us away for a week in this, and they just think great thoughts. And I was in charge of the sensors panel. And the sensors panel is how do you think about sensors in the future? And not only how do you sense things, but how do you sense that you're sensing things? How do you sense that other people are sensing you? And how do you sense that they're sensing you and you're sensing back and forth and things like that? How do you determine where the nukes are, the underground nukes? We decided to build a CAT scanner for the Earth. It uses neutrinos. And so you'd have this neutrino detector and things like that, and you just do this CAT scan thing around the Earth, and you'd find out where these, anyhow, those are the kind of things we're thinking about.
Until you find the nukes.
But one of the things we wanted to track down is, let's say there's somebody you're trying to find on the Earth. What was the best way to do it? Well, you go to this is during the Cold War period, guys, remember. And so you go to the embassy party, there's this Russian diplomat that you meet and you shake hands with him, and then you put your hand inside your coat pocket and you press your hand onto a meat patty, like a hamburger meat patty, right? And you have that in there, and then you take it back to the lab and you extract out there basically the pheromones of this person, and you create an monoclonal antibodies associated with that particular signature. And then what you do is you send your satellite over and you send you spray this special stuff around, this sort of filters down, and your satellite looks at this glowing path where this guy takes on the Earth. Any rate, pheromones are important, and each of us have our own signature. There are easier ways to do it, by the way, guys. But you have to understand this was during the sort of getting into the late evening when coming up with these things. But in addition to these direct interfaces, we have electrical signals too, electromagnetic signals. Anytime you have charge running around in the body, guess what? What happens when charge moves from one place to another?
Magnetic.
Loss of energy.
Well, you have an electromagnetic field that's created. Guess what? We can pick that up. And also we have this engine inside of us, this metabolism that's taking place. We're burning 550 BTUs an hour. And
Metric.
I don't know what it is, metric. Remember, this is before, the Brits really did a number on us with this. We're still locked in this, here, never mind. That's another whole thing. We still have, when I took thermal, we had to do it in British thermal units. But you have all these indirect things too. The indirect things have to do with the connections that are being made at those other levels. So in designing the interface, you have to think about the direct and indirect. So my last slide is your assignment for next week. What I want you to do is pick one day before next class period, one day. I don't want you to write down all the interfaces you encounter during that day, using the definitions that I've seen. Write them all down. I want you to pick one of them to critique. What you like about it, what you don't like about it, perhaps how you would improve it, okay? And then bring it to class on next Thursday and we'll talk about it, okay? Be same time at 10 o'clock next week, okay? And we'll be getting into the human side of interfaces. Any questions, discussion, things like that?
I was thinking in this book from Donald Norman about emotional design and the daily life things. I suppose that in the 80s and in the late 70s, people was not thinking so much about the emotional connections between the objects and the visitors. But now there are research focused on that.
Yes.
It's really
very much so.
Aspect in the design of the interface.
Yeah, there's two kinds of ways to think about it. One is the likability side of things that we were talking about here. But there's another whole side. There is a whole new field arising called Kansei engineering. I don't know if you guys have heard of that. Kansei, K-A-N-S-E-I. I'm probably not pronouncing that correctly. It's a Japanese term There's not a direct translation into English, but it means sort of the essence of things, the beauty, the friendliness, sort of it's how you really sort of feel about things. And they have gotten to the point where they've created a way to engineer products using Kansei engineering and engineer buildings. You walk into this building and you like it. Or you go in a car, you sit in the car and you put your hands on the steering wheel and you look around and I like this. Well, why do you like it? I don't know, but I just like it. It's one of those things you cannot necessarily express in words. It's just the feeling that you have for it. And so what they've done is come up with a systematic way of pulling these things out. And as a matter of fact, the Mazda Miata was designed using Kansei engineering.
But it's some kind of science or engineering? Because I remember my past courses in the master course in Mexico, and we talk a lot about the rhetorics of the objects, how the objects combines you to use them. And it was more like the humanistics and feelings and philosophy than science.
Yes.
So this approach is...
Well, this is an engineering approach, actually. This isn't even science. I mean, this is how do you get at people's feelings in a systematic way so you can design around it. What are the eigenvalues of an interface in terms of the way you feel about it, and how you can manipulate those things in order to optimize it. So there's this emotional attachment that you have, like my iPhone. I mean, I have this emotional attachment to my iPhone. I can't explain it, but I just sort of like it, and I like what I can do with it, and I like the way it responds, and I mean, Microsoft Bob. Remember Microsoft Bob? Microsoft Bob, or Clippy, the little paper clip thing. I mean, this was an attempt to be helpful and to add this essence of making the computer more human-like, rather than humans computer-like. But it failed. It failed big time. And so you have to be careful about this whole thing. I mean, there was a time when Coca-Cola had their Coke machines that would talk to you. And it didn't last very long. When I was working on a project for the Air Force. It was called Project Forecast 2, where we were locked away near the Pentagon for a year thinking about the future. And this was a high-tech building. And in this building was this high-tech elevator. It had monitors on it and things like that. And it would talk to you. You'd get into it and it'd say, hello, good morning, temperature is such and such, and things like that. And every week, the speaker was gouged out of that elevator. Somebody had taken a knife to it. Turns out people just don't want their elevators talking to them, nor do they want their cars talking to them. Well, good morning, Mr. Furness. How are you today? And I mean, Toyota did this for a while. Didn't last very long. It's supposed to be customized. Your car actually knows you. Good question. Good question.
When I listen to everything talk to me, and I go totally freaked out by it.
Yeah.
Like elevators, escalators, cars that drive like the garbage trucks driving backwards, saying, "I'm gonna turn left. Look out! I'm gonna turn left." But I guess
It could be, yeah. Well, it probably is a cultural thing. It's what you get used to also, I assume. Turns out one of my students, one of my PhD students, actually worked at, what's the name of the telecom research outfit in Nara? ATR, yeah, sorry, ATR. He was working at ATR. And one of the projects they're working on is why ATM machines weren't being used that much. And the people would not stop at the ATM machines. They wanted to go in to see one of the tellers at the bank. And they go up to the teller, and the teller still had an abacus. And they do the calculations on the abacus and things like that. And people did it. And Joey went in and he looked at all this and he said, what is going on here? And he looked at the ATM machine and he says, Well, it's because they can't go through the ritual, bowing and all this kind of thing. And so what he did is he had them redesign the ATM. So there's this little person who recognized when you're coming close. This little person would say something to you and bow. This little person would bow. And you see all these people bowing to this machine. You know, they come in and they bow back, you know, and then they started using it. They started using the ATM machine. So this one cultural thing that was part of their, ingrained in their life, you know, that had to do with connecting.
But I remember that in the biography of Steve Jobs, he said something, and other books I read about that, that they design for, like you say, the archetypical user, because they don't find difference that how the people are going to use an iPod if they are living in Turkey or Mexico or USA or Europe, because they're going to adapt to they have a really, really soft learning curve to use the devices.
Right. But that's only true if it's intuitive. I mean, if it's universally intuitive.
But, you know, it's not really conditioned by the cultural factors. I mean, what's more important that people try to adapt their cognitive process to use some kind of device, or designers. That, by the way, designers have as well a cultural background, and you can see, for example, when the people is designing robots, are completely different robots coming from Japan than coming from USA or Germany. And how this factor influence in the design of the things is something that they consider really, you know, they do a really good effort to try to consider this thing when they are designing, or not really. They say, let's gonna do it this way, and all the people are gonna try to use this thing because it's really cool thing, and they do the effort to learn how they're gonna use it.
I don't know, what do you think?
I guess I reckon groundbreaking technology like that, if there's no current, like, you know, emotional stigma around it, like if you're one of the first, you're going to be creating that, and people are going to pick that up, and this is going to be it. So if you don't do it correctly from there, then you're going to have this failed encounter.
Well, there are some things. I mean, like the Siri thing on the Apple, on the iPhone, you know, didn't work too well in Australia to begin with, and outside of the U.S. Some parts of the U.S. didn't work either, like the poor Southern people like me. And so there has to be some tuning that has to do with just the way, with language and with and I know cultural colors mean something different in Japan, you know, than they do in the U.S. or in the Western world. And so I think there has to be some tuning. But the point that you were making, Rory, about if you're out there at the beginning and you're blazing the trail, you know, you get to sort of define that. I mean, yeah, sort of invent the culture, because nothing exists at that time. Now, it could be that if it's not good, I mean, if it fundamentally, intrinsically is not good, it's not intuitive, not easy to learn, it's not very efficient, things like that, something else will take its place. So you have to be sort of good to begin with if you're going to set the standards.
That's what makes this course important.
Right. But I think that this is, in the next 20 years, you know, more and more code is being dedicated to supporting the interface. When you think about the capacity of a machine, you know, it's all about supporting the user now. Boy, that didn't used to be that way at all, but now it is. And so I think the design component and the ability to assess the goodness of these things, and I'm going to talk a little bit later about assessment tools. You know, we really are in the dark ages in terms of tools to use for measuring the goodness of these things.
And what about the people? You know, you say that the interface is going to change in the next years, but I suppose in consequence of this change of the interfaces and the cognitive process that are involved in these interfaces, people are going to change as well.
Well, I think people are going to cause it to change. I mean, when you think about it, I mean, the demand is now, in a way, outstripping the supply. Before it was the other way around. You know, you could do more stuff but now people caught on. You know, now they're looking at interfaces. They'll say, "Well, this is a poor interface." You never heard that before. You know, I have this toaster oven back in the U.S. that I can't believe it. I can't believe they got away with it. It's so poorly designed. And the one they had before was really simple. Same company. Really simple, straightforward.
How do you mess up a toaster?
Yeah, well, that's what I said. You know, how do you mess it up? But they did. A toaster? Come on. And so, you know, and then of course the people who write the manuals. Yeah. But if anybody ever goes to read, when you have to go to read the manual, it's pretty bad. You know, and running a toaster especially.
What do you think that's doing to the overall intelligence level of humans? Basically, if they're not allowed that opportunity to explore something complex, they're not really creating that brain structure that's, you know, like allows higher intelligence. They're just limited to this real basic thing, like an iPad or iPhone. They're not getting that skill that can sort of help them.
Well, yeah. I mean, this is a very good point. Do you ever see this as an old movie called Never Ending Story?
Yes.
It's all about when you lose your imagination, when kids lose their imagination.
I didn't.
And we're sort of doing it, you know. When we make movies about Lord of the Rings, gosh, I had this great world built in my head from reading the books and just creating those worlds and that through the imagination. And then the movie comes along. It's good movies, but they just screw up my world that I had built. And that's one of I gave a talk to the Washington Tree Fruit Growers Association. And these are the people that run apple orchards and things like that in the state of Washington. This was sort of one of the things that the university wanted me to do to build goodwill with the other part of the state. And so I went over there talking to these farmers. And I told them about virtual reality and all the stuff that's happening, things like that. And these parents came up to me after and said, "Oh, this is amazing. What should we be teaching our kids? What should we get them to take in school? You know, what courses should they take and things like that in high school? Should they, you know, more physics, more math? You know, what?" And I said, "No, get them to read the classics. You know, there are a million virtual worlds, and that, you know, that are in the classics, and use imagination, because there is no one who owns this field. It's not the computer scientists. It's not the engineers. It's not even the storytellers. It's one of those things like nanotechnology. Who owns nanotechnology? It cuts across. And so UX cuts across all of these things, I believe. And so we got to be responsible in our use of technology. It's so easy to get intoxicated by it and to do things just because we can do it, not because we should do it. And this is one big thing of how we are taking away imagination. I mean, the magic book stuff. We're talking about 3D pop-up books, you know, when we used to have those in our head. We used to create them on our own. And now we sort of do it for it. Now, there are things you can do with teaching math, teaching physics, chemistry, things like that, that would be powerful using that. But that's what's the ambiguity in all this. So we got to figure out a way to sort through that. That what doesn't take away what adds, and we want people to learn how to use their hand-eye coordination, you know, and exercise their brain.
It's been documented that people are slowly losing their ability to read maps.
Yes,
Because
I
of
saw that
GPS
as well.
devices.
That's right. That's right.
Yeah. It would seem that the younger generation are losing their ability to spell.
Yes. Yeah.
So is it sort of important when you're designing these things maybe to allow for some affordance to expand? Like not only you've got an easy level, but then you want to progress. So you want to make you want to have more features or something. Be able to do more with it.
Well, I think one of the solutions is where you put the design in the hands of the user. So that, and to some extent we do that now with our, my desktop on my computer looks different than your desktop, and the scripts I put in are different than, so each of us have some way to customize our interfaces, but wouldn't it be cool to allow people to have the toolkits to construct these kind of things? And some would, some wouldn't.
I just hope that the generation picks up on that, because if they do that, then they will become powerful in that way. If they don't, we'll have people who are like, now I'm stuck in this one mindset. I can only use it this way. If it's changed, then I don't know how to use it. It's going to be
Yeah.
might want to use it. That'd be a real shame if it happened.
Yeah.
Which already happens.
Yeah. Well, and a lot of people will say, yes, but this is just platforming. You know, the fact that you have your calculator now and you have your computer, all this kind of stuff, you don't need to worry about that anymore because the machines take care of all that. You don't need to know how to do long division. You don't need to know how to do square roots, that kind of thing. That the machine will do it all. And so therefore we are now at a higher platform we can reach. We don't have to, you know, start from the bottom here. And so that's one of the philosophies in the use of technology that lets us reach further than we were able to before. So it's a good question if that's what's happens to that. But then there's a book written by, oh gosh, it's a short story called The Machine Stops. It's a famous author. I'll have to look it up and send it to you guys. The Machine Stops. This story about people becoming so dependent on machines, and then what happens if they stop working. This happens in flight, by the way, in the airplanes, because in commercial airplanes, commercial airlines, pretty much everything, the flight management system runs the whole thing from takeoff to landing. And so the pilots are just sort of there drinking coffee, you know, and talking sports to this co-pilot.
They have to land it. Take it off though still.
They can do the whole thing. Computers can do the whole thing. Yeah. And a taxi and take off, the whole thing. Now, but the pilots do, just to get some practice, you know, they do a lot of that manually. But that's the reason why they go to simulators all the time. They have to have so many hours in simulators where they turn off an engine and they cause bad weather and things like that. So pilots have to insert themselves into the system. But it's a real problem as this automation takes over. What happens when the machine stops?
It's the same with surveying. You do all the, if you're doing my degree with surveying, you learn to do all the computations manually by hand. I don't know if anyone's done a least squares adjustment by hand. It's not exactly fun. But then you get into the real world and the machine will do everything. And you don't even need any computer. Oh, you don't need to have gone to university. You just press measure. And like even when you want to put that point back in, big screen pops up. Arrows pointing. Go forward. Go back. You just walk there. And it says, "Put it in now." That's it.
Well, that's amazing. So it's a problem to know how far you go with this and taking away some of those basic skills. I mean, back when I was in engineering school, of course, we had slide rules. And so you had to guess what the answer was in your head because you had to figure out how many significant digits were there. So when you're working the slide rule, it's just going to get you closer to the number, but you had to work it out in your head. And so you knew when you got an answer whether it was in the ballpark. But you don't have to do that anymore. Nobody does that anymore. So you just punch it in, and when an answer comes out, you write down, and you don't think, does that make sense? Yeah.
It's not a matter of thinking. I think there is things which are more technical, and I think which is the things that there are things which machines can do, and these which could be called technical things. There are things which machine can do and human can do, which is I think we rather put more effort on actually things that machines can do, like invention, novelty, and all these things. For example, machines cannot really author a nice novel or a nice poem or a nice song, but they can do a lot of technical things. And these kind of technical things evolve and can change over time. You know, people used kind of like to work from like labor, but manually. You don't need to do it. So you don't even need to think about like what happened if the tractor fails. It's okay. So it can fail, then you can repair it and continue. I think it's the same thing, which is people always can. You need to be conscious about something could fail in critical like things like airplane, but not to take it everywhere. Like you don't like start with something. You tell your friend we are going to meet like later in the evening for coffee. And then you don't immediately think what if you die. So it happens, yes, but I think it should be a balance between like things, and I think you mentioned that we don't need maybe kind of to look behind, just look forward. It's more like what things which is machines can do. It's kind of more, I think we rather like putting effort in there rather than looking back what things that we are losing. But these are all technical.
Good point. But we are tool makers. Humans are tool makers, and we're going to continue to do it. And that's the way we progress in terms of being able to accomplish more. Yeah. Okay, gang. Well, I'll see you then next Thursday, and look for your list. And I'll hold on to these for the time being. You can have your book back.